Assalamu alaikum. My name is Muzammil Tariq, and this is the video submission for CS412 Algorithms Design and Analysis project. In this, it's me, Sayyid Muhammad Abdullah Arif, and Sayyid Muhammad Abbas Haider. We have chosen the problem of string matching for this project. Now, what exactly is string matching? So, in various situations in computers, we have to compare several strings with each other. For example, in plagiarism checking, spam filtering, or search engines, we have to compare strings. So, in just this title, we can see that S and M or T and A, they are not matching with each other. So, in the comparison. So, for example, in spam filtering, when we receive an email, it's broken down into its tokens, and then each of those tokens is compared with a bag of words which is considered to be spam. And through that, a computer recognizes if an email is a spam or not. The same thing happens in plagiarism checking and search engines and several other domains. So, how do we actually match strings? There have to be several algorithms for it. So the most basic way of doing that is a naive algorithm, which just iterates over both the strings and compares them. But of course, it's take a high number of computation. So we improve that by deploying Knuth-Morris-Pratt algorithm and then also Boyer-Moore algorithm. So how does a naive algorithm works? First of all, it takes a complexity of O of m multiplied by n minus m plus 1. M over here is the length of the pattern that we have to search for, and n over here is the length of the text that we have to search in. And as you can see, it's a very large number. It's so large because if we see over here in the example, we first start comparing from the start, and when the comparison fails at this point where b is not equal to a, in naive approach, it starts comparing from the next element in the text. This is a very basic way of comparing, but it clearly takes a lot of extra comparisons. So, in order to improve this, we have to somehow reduce these comparisons. For that, there is the Knuth-Morris-Pratt algorithm. It does the same job in O of n, and what it does is that it makes a pre-computed list which stores the number of skips that we can do. So in the same example as before, we are stuck over here when B and A cannot be matched. So what a Knuth-Morris-Pratt algorithm does is that it does not start comparing from A, rather it starts comparing from B over here, because it knows that A, B, and C were already not equal, but C over here was equal to the start of the pattern. And this list is created in O of M. M over here is again the length of the pattern, i.e. this pinkish purple string, and N over here is the same length of the text, the bluish string over here. Then there is the Boyer-Moore algorithm. What it does is that it uses two pre-computations rather one. One is a bad character rule and the other is a good suffix rule. What it does is that rather than comparing from the start of the pattern, it starts comparing from the end of it, and it basically shifts the pattern at every position. It feels the need to skip some comparisons. It does the same job in O of n m. M again is the size of the pattern and n is the size of the text. The pre-processing of this takes O of m plus is sigma. M is the same length of pattern, and sigma over here is the length of alphabets because it compares the string with each alphabet. Now my group partners Abdullah and Abbas will theoretically and empirically compare these algorithms and also explain how this pre-processing is done and what is the actual algorithm behind these.
Okay, now talking about the theoretical aspect for the performance of these algorithms. First, we will clarify the problem. Our problem is to basically find all the patterns of substrings in a given text. Now, first, let's discuss the naive string matching algorithm. In this algorithm, we basically shift the character one by one and match it with the pattern we have. So we move the pattern character by character throughout the string to find if it matches with any. So this is how its visualization would be. Now to calculate the complexity of the Naïve string matching algorithm, we have to take account of the for loop executions that it takes in shifting the pattern string and the number of comparisons it performs within each iteration. So the worst case would be the product of these two variables. Now, next we have is the Knuth-Morris-Pratt algorithm. In terms of the Naïve algorithm, it can reduce comparisons by backtracking whenever a mismatch occurs. Now from education.io, I will show you a visualization of how that is. So this is how the Knuth-Morris-Pratt algorithm goes about. So we have a text and a pattern, and we have pointers to the inside each of them. We keep moving on both the pointers and comparing the text. In this case, they matched, so we move both of them, and we consequently keep moving both of them until they match. Now notice that within this pattern of matching, we see that at the end we have a repeated C, a suffix that is also a prefix. So when in the next step we will see that A and B will not match. When that occurs, in the case if this scenario was in the case of a Naïve algorithm, we would go start again by shifting the pattern only once and comparing it once more. But in the case of the KMP's approach, we can reduce these comparisons by only shifting to the part where we last had this suffix. So the worst time complexity of the Knuth-Morris-Pratt algorithm is O of n plus n. We got this from knowing that the time it takes for LPS table creation is O of m. This is the table that allowed us to know how much we had to backtrack. And after the processing, the time it takes to actually search is O of n. So the worst time complexity is the sum of these two. Next we have is the Boyer-Moore's algorithm. Now there are two types of this algorithm. There's the bad character heuristic and the good suffix heuristic. In our case, we will be only discussing the bad character heuristic. Now this algorithm this functions by comparing the pattern with the original string, but this time from the suffixes. It starts from the suffixes and it goes back and compares until there's a mismatch. Now in this case, when there's a mismatch, it aligns the pattern text with the main text in a way that the character that mismatched, A, that was the case, would be the last same character A inside the pattern. Where in the case there is no such character inside the pattern, it completely forwards it. In a similar way, we had to pre-process in the Knuth-Morris algorithm the pattern to know how much we have to move, shift, or backtrack. We have to do it in Boyer-Moore's algorithm as well. This is done using calculating the last C function for each character that is inside the main string. So this is done by last C function operates by assigning the index of the last occurrence of the character that is mismatching in P, or the C in the character P in the pattern P if it's the only character that exists in P, and -1 if it isn't present. So here we have an example of such a table below. Now, in the calculating the complexity of the Boyer-Morse algorithm, the worst case running time is O of nm plus sigma. Now, sigma over here is the number of alphabets that are present inside the main string. So, to summarize the basic theoretical comparison between these three algorithms, we find that the Naïve algorithm would work better for smaller sets of data because it does not have any pre-processing. And in the case of the Boyer-Morse algorithm, it works better for large alphabet, but it requires pre-processing. And in the case of the Knuth-Morris-Pratt algorithm, it seems to be working best with binary string. We should expect it to work best with binary string, and it requires pre-processing. So now Abdullah will explain the results of the empirical testing.
Assalamu alaikum guys, my name is Abdullah Arif and I will be discussing about the empirical part of our project. So here are the libraries that we have imported for simulating our data, and this is the algorithm that we have written for Naïve, Knuth-Morris and Boyer-Moore, which have already been discussed by Abbas. Moving on to the simulation part. So in this word generator function, what we are actually doing is that we are randomly generating a string of size n. The strings being generated are both alphabetical as well as binary. Moving on to the complexity and the complexity n and complexity m function. So in these both functions, we are initializing a list in which time is being appended, the time taken list which can be seen. For the case of complexity n, what we are doing is that we are keeping the pattern constant while we are increasing the size of text with every iteration, which can be seen over here in this loop. And for the case of complexity m, we are keeping the text constant while increasing the size of pattern in each iteration. Moving on to these next two procedure functions, n procedure and m procedure. What we are doing in these functions is that we are using these functions to plot our graph. Since the values of n and m we have taken are very large, because of which I'm going to show you the simulation I have already done. So this is a simulation in which we are comparing the time taken by each algorithm to match a string containing alphabets only. Since Boyer-Moore performs the best with large string, it can clearly be seen that it has the best complexity, whereas it can also be seen that Knuth-Morris performs the worst in with large alphabetical strings. This is the simulation this is a simulation in which the string is binary string, and it can clearly be seen that Knuth-Morris is taking the lead, as Knuth-Morris performs the best if the strings are binary. Finally, moving on to the last simulation, this simulation is the comparison of size of pattern. In this simulation, we can clearly see that with increase in length of the pattern size with increase in the length of pattern, Knuth-Morris becomes less efficient, whereas on the other hand, Boyer-Moore and Naïve becomes more efficient. That's it. Thank you guys.